Welcome to today's video where we're gonna start talking about a new topic that we will call stability. And it promises to be very interesting and is fundamental in engineering. So, to begin with, let's introduce a couple of concepts. This is the video today is gonna be about the transfer function and the impulse response of a system. Now, imagine I have here, consider the following differential equation, linear, of constant coefficients. You have the nth derivative of x, coefficient an, the n minus 1 derivative of x, all the way to the first derivative, and the zeroth derivative equals u of t. Now, what is this? I think the harmonic oscillator is an example of that, right? A second order equation. If you write something like this, I don't know, like x dot dot plus, let's just write, I don't know, x dot plus x equals u of t, right? This thing would be a harmonic oscillator, for example. And you see here that the u of t represents the input, the force, right? What am I applying? What is driving the system? Remember, the harmonic oscillator is the external force. In the RLC circuit that we did, that was the signal, the voltage, the signal generator, remember? The source that you connected to the RLC circuit. So it's like the input. This u is the input. And then x of t is the output, so given some forcing, some input into the system, how will my system react? Given some force that I apply to the mass, how will the system oscillate if it's an oscillator? Given a signal generator that I connect, I have a square pulse or something like that, what would be the response of, for example, the voltage in the capacitor, you see? So we have an input and an output, and this is the way we relate, we think about many engineering systems, right? You have put something in, you get something out. You put something in that you can do, and you get out something that's useful. All right? Okay, so given a system like that, again, it could be anything. It could be any system. In this case, a linear system. But it could be, by that I mean that the equation is linear. The differential equation that characterizes how the system responds in time, it's linear. And then we have here a force, and then x will react, whatever the system reacts. We define the transfer function that we call g of s. So the definition of the transfer function, it's going to be made in the S domain. It's important that we actually give the transfer function also in the T domain, so we will talk about that a little bit. But in the S domain, that means in the Laplace domain, okay, is the ratio of the Laplace transform of the system output, x of t, the response, that's the solution to the system, and the system input, or the forcing term, right, the forcing function, or the driving term, the driving function, etc., u of t, right? Under the assumption that the system is at equilibrium, at zero initial condition. The system, if it's a harmonic oscillator, we have zero, it's at equilibrium with zero velocity, zero acceleration, etc. Okay? All right, so the definition of this, let me just write it, is G of S is defined as capital X of S, right, the Laplace transform of X, the response, divided by capital U of X, which is the Laplace transform of the input. All right, well, we can actually make this a little bit more general, and we can actually write, instead of this forcing term that is very simple, that depends only, the system takes as an input, some input function, we could have that the input is made of some function that I can control, and then also its derivatives, just to generalize a bit. Let me do it for a second. So what I added here is, on top of having, the case before was b0 equals 1, and then all the b1 up to n are 0. But I allowed here that my input, whatever my input is, it contributes to the driving also through its derivatives. This is to allow for more general systems. In circuits, for example, would be that you have your input, but you also connect a differentiator to your input, so you get the two signals constructively. And then the input, what you can actually control, will also be the contribution to the driving from the input will also come through derivatives, right? This is just a bit more general than I wrote before. Now, if we do that, of course, we need to add also the conditions here that u of 0 equals u dot of 0 equals all of them, all the derivatives equals 0. Okay. All right. So, to get the response function here, it looks, if I look at the definition, looks like I'm going to have to find x and then find x of s, and then find u of s by transforming. That feels like a lot. But not really, because we don't have to do it. Let's see. How do I get g of s from 1? That's the question. All right, so to see how I get it, let's Laplace transform both sides of the equality. Now, this is particularly easy because we have a theorem that tells me that the transform of the derivative, let me write the little theorem here. Maybe I'll just sum on the theorem and I'll put it there. How about it? So, this theorem tells me that the Laplace transform of the nth derivative of a function is s to the n times the Laplace transform of the function minus s n minus 1 by the times the function at 0. S minus s minus s to the n minus 2 times the first derivative of the function at 0. And then I go all the way to the n minus 1 derivative of f at 0. Now, the cool thing here is that if I do the Laplace transform of this term, I would have to have everything, all the terms in here, but under the assumption that all the derivatives are 0, this simplifies. So this thing is equal to just Sn f of s if all the derivatives equals x dot of 0 equals 0 for all the derivatives. If all the derivatives are equal to 0 at 0, then this just simplifies to Sn times f of s, s to the n times f of s. Now, that means that if I take Laplace transform of this and Laplace transform of that, so let's Laplace transform both sides of 1, that yields the following. All right, so I get Laplace transform of x, let me just write it, an times s to the n Laplace transform of x of t, which is capital X of s, all right, plus an minus 1 s n minus 1 x of s plus blah, 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 all the way to a0 x of s. And the same happens on the right hand side. I get bn sn, and then I get capital U of s plus bn minus 1 s n minus 1 capital U of s plus blah, 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 all the way to b0 u of s. Now the nice thing is that I can get factor x of s here multiplying everything. So it is, if I were to write it, that would be an sn plus an minus 1 sn minus 1 plus blah, 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 all the way to a1s plus a0, okay, multiplying capital X of s, and then I get the same thing here, bn sn plus blah, 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 plus b1n, sorry, s plus, oh, the one goes here, sorry, b1s plus b0, multiplying u of s. All right, that's what I get from the Laplace transform. And then I can solve for the transfer function directly from here, and I get that the transfer function g of s, which is equal to x divided by u, so I put the u here dividing, so that would be x of s divided by u of s, right? I put this here divided, and I move this one here divided, and I get the ratio of these two polynomials. So I get bn sn plus blah, 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 plus b1s plus b0 divided by an sn plus blah, 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 plus b1s, oh sorry, a1s plus a0, and there you go. So the transfer function, to write the transfer function a1s plus a0, sorry about that, to write the transfer function, I don't need to actually solve the system. I can get it out of the coefficients in the original equation, the coefficients of the derivative of the function and the coefficients of the input and its derivatives. Now this is kind of cool because the transfer function that's telling me the ratio is kind of, remember what it is, the transfer function tells you the ratio between what you get over what you put in. And that ratio, to compute it in a linear system, I don't need to know what you get and what you put in. I can do it out of the coefficients of the equation. Which is kind of neat because you see, it written like that, it's pretty clear that it does not really require you to know, if you want, it doesn't require that you know exactly what the input and what the output are in order to compute the transfer function. The transfer function is something that's, that depends on the system itself. It doesn't depend really on the particular solution of the input. It's a relationship between input and output. All right. Now, let's do an example of computing one, and then we will try to understand better what this transfer function really is. Let's do an example quickly. All right, so we have this exercise. The response of a physical system x of t to a driving u of t is governed by this equation, right? So it's driving, you put an input, force or whatever, and then the driving is given by 9 times the input, negative, and then 12 times the derivative of the input, and the system responds consequently. Depending on what you do as input, you can do like punching it, or very, very soft and do different things. You can put a cosine, you can put a heavy sine, you can put whatever you want. But remember, the transfer function does not care. The transfer function informs you about the equation, regardless of what the solutions are with the driving that you put in. So it's independent of what you put. It's how the input and the output are related. And again, remember this: the transfer function in the S domain is defined as important the ratio of what the system does, Laplace transform, the response of the system, Laplace transform, and the input, Laplace transform. Now, this kind of suggests that you need to know the solution and you need to know the driving to compute it, but we proved that that's not the case. We can do it without. Let's do it by take Laplace transform of, let's call this equation 1 under the assumption that x dot dot of 0 equals x dot of 0 equals u dot of 0 equals u of 0 equals 0. If we do that, we get that the left hand side becomes s squared capital X of s minus s capital X of s minus 2 capital X of s equals 12 s capital U of s minus 9 capital U of s. Right? There would be extra factors if these weren't 0 with the initial condition, because they are 0, they're not there. Now, of course, we can now factor everything that multiplies x, everything that multiplies u. So x of s is multiplied by s squared minus s minus 2. And then this is equal to u of s, capital, multiplying 12s minus 9. Now, all that I need to do is move this into this denominator. Here's the transfer function, and put this into this denominator, and I get that the transfer function in the S domain is 12 minus 9, 12s minus 9 divided by s squared minus s minus 2. So this is half of the solution because that's the transfer function in the S domain. I want it in the T domain. Now, before going to the T domain, let's realize of something. The denominator of the transfer function happens to be the characteristic polynomial. Remember, if you were to find the characteristic polynomial, it would be lambda squared minus lambda minus 2, s squared minus s minus 2. That is the characteristic polynomial. So, little hint, the transfer function is going to be divergent. It's going to have what we call a pole when s is equal to one of the roots of the characteristic polynomial. So that's kind of this function has so much information about the system, and this function actually kind of goes to infinity when s is equal to the roots of the characteristic polynomial. What a coincidence, right? It's not a coincidence. By now, I already said it was a coincidence in previous videos. It's not a coincidence. I was a little bit mysterious about it, but now you see that maybe it's not a coincidence, because this transfer function, it's really getting information about the system. Anyway, before getting to understand better that, let's finish the exercise. The solution is g of t, which is of course the inverse Laplace transform. Wow! The inverse Laplace transform of capital G of s. Right, and for that we need to do a very simple fraction decomposition. So let's just write this thing, 2s minus 9, that's g. So let me just write this is gs. gs, of course, is equal to 12s minus 9 divided by, let's write it to factors. You can use the quadratic formula, minus b plus minus square root of b squared minus 4ac divided by 2a, but this one is very easy to eyeball. You can quickly see that negative 1 is a root. 1 squared is 1, minus 1 is 2, minus 2 is 0. So s plus 1, because minus 1 is a root. And the other one is positive 2, because 2 squared is 4, minus 2 is 2, minus 2 is 0. So the other one is positive 2, so s minus 2 is the other factor. Okay, cool. So that means that I have two simple fractions, s plus 1 plus b, s minus 2. It's good practice. I'm doing the whole thing because it's a simple one. Common denominator gives me a s minus 2a, all right? And then plus bs plus b divided by the common factor, s plus 1, s minus 2. All right, this is equal to that. Denominators are equal, so numerators have to be equal too. And I get the following equation. As plus, or minus, sorry, minus 2a plus bs plus b, it's equal to 12s minus 9. Wonderful. I equate coefficients on both sides, and I get the coefficients of s to the 1. That gives me a plus b equals 12 on the other side. The coefficients of s to the 0 gives me minus 2a plus b equals minus 9. All right, this system of equations is very easy to solve. The easiest way to do it is, let's subtract the second from the first. If we subtract the second from the first, I get 3a, b cancels, equals 12 plus 9, so 21. All right, nice, so a is 7. And then I use this one, for example, and I get that 7 plus b, well, b is equal to 12 minus 7, which is 5. Right, very simple. So I got my simple fractions. Capital G of s, it's equal to 7 times 1 over s plus 1 plus 5 times b over s plus s minus 2. All right, so now finding g of t is very simple. It's just the inverse Laplace transform of g of s, as we wrote already up there. And that thing is 7 times the inverse Laplace of 1 over s plus 1 plus 5 times the inverse Laplace of 1 over s minus 2. Those are Laplace transforms that we know. This is an exponential, this thing right here. This is the exponential of 2t, and this one here is the exponential of minus t. So finally, the transfer function in the t domain is 7 times e to the minus t plus 5 times e to the 2t. And there we go. That's the solution to the problem. That is the transfer function. This function here contains a lot of information about my system. Now that we've done an example, let's try to understand what this really is and why it's so important and how something so simple gets so much information about my system regardless of what I put as an input or an output. Let's do that. The question we're going to answer now is, what does the transfer function do for you? So what is it? What kind of object? How do I see more clearly how much information it unpacks about the dynamical system? Now this is kind of easy to see. So remember, the transfer function in the S domain is the ratio of the Laplace transform of x over the output over the Laplace transform of the input. And remember that to compute it, I don't need to know the input and I don't need to know the output. It's independent of the input and the output. It's only dependent on the equation, on the coefficients of the equation, remember? Right, and remember that the transfer function, the t domain, well, is the inverse Laplace transform of the transfer function in the s domain. Right, so now let's see. So what is x of t? X of t is the output. Remember? Is the solution to the equation. Now this thing, of course, is the inverse Laplace transform of capital X of s, the Laplace transform of the solution, or the output. But using this, it's clear that I can put this u here, and x of s is actually g of s times u of s, right? So this thing is the transfer function, g of s, times the input, right? I just put this here in the equality. I did that substitution. Interesting. But this is the inverse Laplace transform of the product of Laplace transforms. Remember the convolution theorem? The convolution theorem tells me that the product of the two transforms is actually equal to the transform of the convolution. So using the convolution theorem that we saw, we get that this thing is small g of t convolution with u. Remember? That's it. So here, let's call this equation 1. So here I used 1, and here I used I'm going to put it here, the convolution theorem. The else cancel, and I get that this is g of t, u of t. So let me write it here. X of t, the solution to your system given an input u of t, this thing is exactly equal to the convolution of g of t with u of t. Or in other words, it's an integral, the integral from 0 to t, because they're causal functions, g of eta, u of t minus eta, d eta. This result is really important. This result tells you what the transfer function is. The transfer function is an object, a box if you want, that takes the input and returns the output. And from the input, put the input you want through convolution with the transfer function, you get the output. The convolution maps the output, the transfer function maps the outputs into the inputs. So let's think again about it. The transfer function is an object that says, okay, give me your input. I'll do the convolution with myself, and I'll give you the output. And you see, this thing, the transfer function, only depends on the system dynamics, not the particular input. So the solution depends on the particular input. Of course, if I kick it with if I watch TV and I just kick the button, I press the button gently to switch it on, or I just kick it with all my strength, the output is going to be different, right? However, the transfer function, these two things depend on the inputs. This is the input itself, so of course it changes with the input because of the input, and this depends on the input because the output depends on the input. But this g of t doesn't. It's only a function of what differential equation governs your system. So you see the solution has part of contribution to the input, so the input determines the solution, but also a part that is given by the dynamics. So the transfer function tells you how to relate an input with an output through the convolution. So the convolution integral is important, you see. The transfer function that characterizes your system, that to determine it, you don't need to put any inputs and you don't need to compute any outputs, you can determine it directly from the equation. It's the map that takes inputs into outputs through convolution. So looking at the equation, if I want a solution, all that I need to do is the convolution between the input and the transfer function. Find the transfer function, get the convolution, get the input, and do the convolution, and you'll get the output. But of course, you see that seems much easier than all that we've done. But actually, remember, we've done, because what is easy to determine is the Laplace transform of the transfer function, capital G of s. Then we need to invert the Laplace transform to find small g and then do a convolution. So we're doing a similar amount of work to get it, but it's kind of conceptually really cool. The transfer function is the key to translating inputs into outputs. All right, so I hope that this is clear, and I hope that you are like, I don't know, you're enticed by this to think more about it, and we get to discuss it in our review sessions. Let's see one more thing before we finish this video. All right, the concept that we're going to see right now is called the impulse response. Impulse response is the response of the system when the input is a Dirac delta. So we make u of t equals a Dirac delta. All right? Now, this is going to be quite interesting because the response of the system, which of course depends on the input, in this case is going to be very easy to relate to the transfer function that, remember, does not depend on the input. Okay, let's see it. So, look, the transfer function is x of s divided by u of s. These two things, this depends on the input, it depends on the input, but the ratio doesn't. The ratio Laplace transform doesn't. But let's take the particular case where u of t is equal to a delta. Well, in that particular case, I know that the capital U of s would be 1 because the Laplace transform of the delta is 1. Remember? If you don't remember, you quickly go to the definition and write the Laplace transform of delta of t is, right, the integral from 0 to infinity e to the minus st delta of t dt, and that means that, well, delta here is delta of t minus 0, so this all gives me this function evaluated at 0, so this is e to the minus s times 0, so this is 1, okay? We proved it already, but if you don't remember it, it's good to do it like that. All right, so if mu of t is a delta, then capital U of s is 1. And in that case, it happens that x of s is equal to g of s. So the Laplace transform of the response coincides exactly with the response function if the input is a delta. Remember, the response function is the same no matter the inputs, but if the input is a delta, it so happens that the output is the transfer function. That also means that x of t would be equal to the inverse Laplace of g of s, which is the transfer function in the time domain. Of course, if they're equal in the Laplace domain, they're equal in the s domain, they're equal in the time domain. S domain, I call it Laplace domain, t domain, I call it here time domain, all right? All right, so this is actually pretty easy to see if you want, because you can do it like that. You can also do it by the result that we got right before, that x of t is the convolution of the transfer function and the delta and the input, right? If the input is a delta, right? What I get here is, all right, this select the value eta equals t, and this only gives me g evaluated at t, g at t, right? You can say it like that as well. I will prove it in two different ways. All right, so nice. If I drive my system with a delta, then the transfer function, so then the response of the system happens to coincide exactly with the transfer function. So this is kind of nice because, right, it's kind of nice, right? Because that gives you an experimental way to measure the transfer function. So how do I measure the transfer function? Measure the output of the system when you kick it at time equals 0 with a delta. Remember what a delta does is kicking it. So it's like, okay, at time equals 0, I kick it and check the response of the system, and that is the transfer function. So you can measure the transfer function experimentally by driving it with a delta. So the impulse response is exactly equal to the transfer function. By the way, little note. You may have noticed, of course, I've told you that f of x delta of x minus x0 dx equals f of x0. When this is including the domain, for example, I don't know, I mean, let's do minus infinity to infinity. Okay. Now, you may wonder, because you've seen it right now, if f of x delta of x0 minus x dx is also this. And the answer is yes, because the delta is a symmetric function. Delta of x equals delta of minus x. All right? Think of it as, of this Gaussian function that was getting taller and thinner. So it's a symmetric function when it gets to the limit, right? This is 1 point, so it's very symmetric. All right. Anyway, let's do an example of calculating the impulse response and also calculating the transfer function in the way that we learned before, and compare them and see that they're the same. All right, so find the transfer function and the impulse response of a system governed by that equation. Right, remember, for transfer function and impulse response, the assumptions are always that x dot of 0 equals x dot of 0 equals x of 0 equals 0, and then in this case only one u of 0 equals 0, right? All right, so first let's compute the transfer function. Okay, for the transfer function, as I have here, I get the following. For the transfer function, I get Laplace transform of both sides. So if I Laplace transform both sides, I get s squared x of s plus 5 times capital X of s, s capital X of s plus 6 capital X equals 5 capital U of s. Alright, so I group X of s here multiplies s squared plus 5, there's always 5s in these problems, 5s to make my life worse, plus 6 equals 5 times u of s. Now of course all that I do is I put the u in here, so I get the g of s, which is of course capital X of s divided by u of s, and that's equal to 5 times s squared plus 5s plus 6. Look at that, the characteristic polynomial is the denominator. Right, the poles, the points where it diverges, right, the poles of g of s is always the characteristic polynomial. It's the roots of the characteristic polynomial. All right, so that's the transfer function in the Laplace domain, right? In this domain. So let's make it to simple fractions. I'm gonna do it very fast. This thing is 5 times 1 over s plus 2 minus 1 s plus 3. Those are the two simple fractions and its coefficients. So I do small g of t, which is the response function. It's equal to the inverse Laplace of capital G of s. And that's easy because it's 5 times the inverse Laplace of 1 over s plus 2. Inverse Laplace, sorry about that, minus the inverse Laplace of 1 over s plus 3. Alright, so this is easy. This thing is the exponential of minus 2t. This thing is the exponential of minus 3t. Okay, so finally, g of t, where should I put it? Because I want to do the impulse response here. Okay, so I'll write it here. G of t, it's equal to 5 times exponential of minus 2t minus exponential of minus 3t. And that is the transfer function. All right, and we computed, remember, the transfer function does not require you to put an input. This is the transfer function for the system. It's the same if the input is a cosine, it's a hyperbolic tangent, it's a square root of 27t, or it's a delta, an impulse function, a Dirac delta, right? It doesn't care. This is independent of the system, it's only characteristic of the system, it's independent of the input. Now let's compute, this is the transfer function calculation, transfer function. Let's do the impulse response. The impulse response is solve x of t when u of t is equal to delta of t, and of course under the same assumptions. X dot of 0 equals x dot of 0 equals x of 0 equals 0. All right. But no assumptions on the u in this case because it's given. You cannot make assumptions on things that are given. Okay. All right. So let's do it. So when we do that, we have the equation that we get. Let me just write the equation in this case. This x dot plus 5x dot plus 6x equals 5 delta of t. Let's take Laplace on both sides. If we do that, the left hand side is exactly the same. S squared x s plus 5 s x of s plus 6 times x of s equals 5 times the transform of the delta. The transform of the delta is 1, so it's just a number 5. Okay? All right. Now, of course, we do the common factor. Capital X of s multiplies s squared plus 5 times s plus 6. That is equal to 5. Oh, wonderful. The solution in the s domain is, oh, look at that. What it's going to be? It's 5 divided by s squared plus 5s plus 6. So this is in the s domain. Now, of course, I need to compute x of t, which is the inverse Laplace transform of capital X of s, which is the inverse Laplace transform of that fraction there, 5 divided s squared, wow, s squared plus 5s plus 6. But we've already done that in the previous exercise. And this thing is exactly 5 times e to the minus 3t minus, e to the minus 2t minus e to the minus 3t. And that is the impulse response. Now, of course, this is just to explicitly check that the impulse response is exactly equal to the transfer function. And you see, so every time that I ask you compute the impulse response, compute the transfer function, it's exactly the same thing, okay? Right, so the nice thing about it is that the transfer function, which is something that we develop theoretically, remember, is the ratio between the output and the input, and that is the same no matter what the input and the outputs are, right? For all the inputs possible, you get the output and it's the same transfer function. I give you a way to measure it in a system. So if someone gives you some engineering device and tells you to test it, find the transfer function, you don't need to do math to find it, you can measure. You can measure the output and at time equals 0, just kick it, do a delta driving. And then the response, the oscillations, you look at the oscillations of the system or how the system responds, and that response is exactly the transfer function. The transfer function is the impulse response. Transfer function is the impulse response. Okay, that is the message that we get from that. All right, I hope that we'll learn a little bit about this abstract object called transfer function. You will be hearing transfer functions in your other courses. In circuits, I'm pretty sure that you talk about the transfer function of the circuit. Hopefully you know what it is. Now, this transfer function is the relationship between the input and the output, and it's kind of cool. It's a machine. Let me summarize some of the cool things, all right? Just a second. All right, so I have a quick summary of this, right? The transfer function, which is the ratio between the Laplace transform of the output divided by the Laplace transform of the input when all the derivatives of the output are 0. So the system is in relaxation, at equilibrium, no velocity, no acceleration, etc. And also, well, if you have derivatives as well of the input in the right-hand side, you also need to demand that at 0, there is the driving is 0, right? You don't need to demand that if you don't have derivatives, but when you do, you need to demand it for the input, for the transfer function. Anyway, so the transfer function is this super cool machine that takes inputs and returns outputs. And you find, given an input, you find the output through convolution. The convolution integral of the transfer function with the input will give you the output. To compute the transfer function, you don't need to know the input, you don't need to know the output. It's general, it's about the system, not how I drive it and not what it does when I drive it with that particular function. It's a super cool object. Now, the impulse response is defined as the output when the input is a delta function. Now, we proved that the output when the input is a delta function coincides with the transfer function of the system. So these two things, under the same assumption, of course, okay? Is the impulse response is x of t when the input is a delta function under these assumptions as well. That all the derivatives and the function itself at 0 is the system is relaxed, and then I drive it just with an impulse, right, with a delta. Now, these two things are the same, and because of that, this is a theoretical object that characterizes the system, and it's a super cool theoretical object, takes the input and returns the output through convolution. It's related here with something experimentally measurable, which is how does my system react when I drive it with a delta? So you can measure the transfer function by measuring the impulse response, how the system behaves when I drive it with a delta. Alright, so now we have to wonder what our systems do. When I kicked it a little bit, does the system go crazy or does the system relax? This is related with the topic of stability, which is the next topic and is the topic for the next video. I'll see you there.